what do we never test? We never test on field 1. What are the 3 plots on field 1? AL, BM, and CN. We never test seed C with fertilizer regime M on field 1. So perhaps that could have been the best result of all, or perhaps the worst result of all. But what is good is that if a particular seed is a sort of toxic with respect to just one other property, either soil or fertilizer, then that will come out, because each of the 3 properties has been tested with every other property. Okay, in a sort of 2 at a time way. Okay, this is decent. Last explanation is called washing machines. All right, this one is the most complicated one of all. Oh, try to go fast. Also possible that no, we keep going. Okay, washing machines. All right, an industrial chemist is studying the effectiveness of a number of options for washing clothes. He wishes to compare 3 brands of washing machine, 3 brands of detergent, as well as 3 water temperatures. Oh man. He also wishes to factor in the effects of water hardness. He will use 3 levels of hardness. He would like to match these characteristics as fairly as possible, but does not have the time or resources to examine every conceivable combination. Okay, this is kind of like a hot topic. How much soap do you need to get your clothes clean? Maybe a lot less than people think. There are advances in the strength of detergents, and yet people are sort of hold on to a psychological amount of detergent that they feel they need to use based on the way they were raised, and often these are passed through generations. I read long articles once, a long time ago, about how really everyone could be using like way less detergent. And actually that's important because stuff's kind of toxic, it gets into the water supply, I don't really know what I'm talking about. Also, it turns out that their advances in detergent are so strong over the years that we pretty much don't need to, if you believe this article. I don't, actually. But if you believe this article, we pretty much don't need to wash our clothes on hot temperature, ever. And we're all just wasting massive, it's just an entire huge environmental problem on a national scale or a global scale, that we're all wasting all of this energy heating our water to wash our clothes in hot water when you just get equally good results on cold water. Okay, well, science can tell us these things, and then it's just a matter of convincing people to believe the science. That's the hard part. So that's what we're going to test now. We're going to test 3 different washing machines. Perhaps it depends on the washing machine. Perhaps it depends on the brand of detergent that you're using. Perhaps it depends on the temperature of the water. And then there's water hardness. You might not even know anything about this, and neither do I. But you Envirothon people will know that water hardness refers to, I think, the amount of like minerals in the water. So soft water, I think, is relatively close to being pure water, but hard water has a lot of mineral deposits in it. I grew up in a house with my own well, actually, in the backyard, so our water was very hard, and that was like a thing. Well, as you can see, if you're following this, we have the 3 types of, so we have the 3 brands of washing machines. Let us call those 3 brands, following Gossett's A, B, and C. These are the brands of washing machines. And then we have the types of detergent. So then we have the brands of detergent. Well, let's call those X, Y, and Z. Okay, great. Then let's talk about the water temperature. Okay, here's where we deviate a little bit in a way that's a little bit kind of leading towards the solution. But let's just let the 3 water temperatures be cold, warm, and hot. But let me call those 1, 2, and 3. And then there are the 3 levels of water hardness, which are really like, soft, medium, hard, or something like that. And let me also call those like 1, 2, 3. Okay, and so you will see that now we have 4 different independent variables that we were testing with 3 options each. And so there are going to be 3 to the 4th equals 81 different possible combinations. If you were doing an exhaustive search of every single possible combination of washing machine detergent, water temperature, and water hardness, you would need to run 81 separate experiments. But that is unwieldy and possibly just impossible. And so, what we want to see again is, to me, this is the best way to understand this, is we want to see whether any two of these reacts very negatively. Is there some particular kind of washing machine, for example, which simply cannot deal with a certain level of water hardness? Or is there a brand of detergent that cannot deal with a certain water hardness or water temperature? And so what we would like, despite the fact that we can't run the 81 experiments that we want to run, in fact we have enough resources to run just 9. Is that right? Yeah. We are going to run just 9 experiments. Only. But what we want to make sure is that everything is tested with everything else. Okay, so following the example of the previous problem, let us decide to put A, B, and C, the 3 brands of washing machine. Let's let those be the labels of our 3 rows, and let X, Y, and Z be the 3 labels of the 3 columns. And now I need to sort of fit 2 pieces of information here into the grid. Okay, seems like I can do that. Picture here. Okay. How are we going to do that? Well, I'll use kind of like an ordered pair. Okay, so in other words, let's first fill in, following Goss's example, let's first fill in temperature. Okay, so in other words, suppose I want to make sure that my temperature is being tested with respect to, notice that already, before having done anything, I already have every brand of washing machine is going to be tested with my only 9 tests. Every brand of washing machine is going to be tested with every brand of detergent. So that's good. And now, if I also want to make sure that water temperature is tested with every brand of detergent and every brand of washing machine, then I simply fill in a Latin square here. And the Latin square we'll do is 1, 2, 3. Okay, so we're going to do the 1, 2, 3, 1, 2, 3. So 1, 2, 3. 1, 2, 3, and then this has to be a 1, this has to be a 3, this has to be a 1, and this has to be a 2. Okay, these blue numbers represent water temperatures, so circle that in blue, and good job. We have now tested every water temperature is being tested exactly once with every brand of detergent and every different kind of washing machine. Okay, and now we shall fill in the information about water hardness. Okay, so let's do that. So I'll add a sort of a second number to my ordered pairs, and the second number is going to refer to water hardness. I will use red. So what does he do? 2, 1, 3, 2, 1, 3. Okay, so 2, 1, 3. 2, 1, 3, and then let's see, that has to be a 2, so that's a 3, so that is a 2, and that's a 1. Okay, well, looking at those red numbers, they do form a Latin square. And so we have succeeded in testing every level of water hardness with respect to every brand of washing machine and every brand of detergent. Because each of the red numbers appears exactly once in each row, and each of the red numbers appears exactly once in each column. It's a great explanation. However, there is a flaw in this experiment. So this is like attempt 1. The flaw in this experiment is that even with the fact that we've only doing 9 experiments instead of the full 81, we have not made full use of the options at our disposal. For example, you may notice that in these 2 cells, we have kind of wasted a run of the test, so to speak, by testing water temperature 1 with water hardness 2 twice. In fact, 3 times. we have tested water temperature 1, which I guess was cold, with water hardness 2, which was medium. And by a kind of pigeonhole principle type situation, if there are 3 options for water temperature, 3 options for water hardness, then there are going to be 9 combinations of water temperature and water hardness. That's clear. And no. Yes, of course. Because 1 can go with 1, 1 can go with 2, 1 can go with 3, 2 can go with 1, so 9. There are going to be 9 combinations of water temperature and water hardness, and we have 9 experiments to run. And if we have over-tested a combination of water temperature and water hardness, it means that something is also missing. And what's missing? Well, for example, 3,2 is missing. And so I'll put a little sad face over here, and I'll write 3. The 3, 2 ordered pair is missing. In other words, we have never tested water temperature 3 hot with water hardness 2 medium hardness. And so this is suboptimal, this attempt. In fact, and I hope you're now seeing what's going on here. In fact, we should strive not only for the blue numbers to form a Latin square, and not only for the red numbers to form a Latin square, but also for the red numbers and blue numbers, when superimposed, to create every possible ordered pair, such that every different kind of water temperature can be tested exactly once with each kind of water hardness. Okay, and so attempt 2 does just this. In attempt number 2, we redo the experiment design. So this is still ABC. This is still X, Y, Z. Give me a minute while I redraw. And I still, I think I'm getting a baby.
Is that bad, or you have to finish fast and move it?
I'm getting Ada.
Well, no, you can finish. Someone has to go get Ada, like.
Alright.
Now.
No?
Or in like 5 minutes.
I will go in 5 minutes. Okay. Yeah. What are we doing? Now I will fill in the blue. I'm just copying this off Gossett. So.
Are you really going to be done in 5 minutes?
No, probably not. Really, no. Okay, I have a baby now. So I will not step on him. Okay, 1, 2, 3. 1, 2, 3. Do you want me to get Ada?
Just go ahead and do your thing.
3, 1. 1, 2. Okay, so is that actually the same as before? It is the blue numbers are exactly the same as before. But now, when I fill in the red numbers, I fill them in with care. I do not just focus on making any old Latin square, but I focus on making a Latin square which also has the property that ordered pairs are not repeated. So let's see if we can make some sense of this. Well, I guess it's sort of arbitrary what goes here, and it's still probably arbitrary what goes here. So Gossett makes that a 3 for whatever reason. Well, now that has to be a 2. So I've just decided to go 1, 3, 2 across the top row for no particular reason. But now, when I get here, I see, well, of course this red number can't be a 1, because there's already a red 1 there. But neither can it be a 3, because that would repeat. And so this now has to be a 2. And then this has to be a 3. And now here, and now I guess we're just going to be done, right? So what can go here? Well, it can't be a 3 or a 2, so it has to be a 1. So it has to be a 3, and this is a 2, and this is a 1. But we have succeeded. Scan, and you will find that, in fact, all 9 ordered pairs appear. Okay. This feature, this is actually an extremely well-written section, in my opinion, by Gossett, because he sort of builds you up slowly through these examples, and now we see, and now comes the theory, and the theory is that we need a way to describe these Latin squares which have this extra added property. And these Latin squares which have this extra added property are called mutually orthogonal. Mutually orthogonal. What are these Latin squares? It's this one, 1, 2, 3, 2, 3, 1, and 3, 1, 2. That's the Latin square blue numbers. And the other Latin square, 1, 3, 2, 2, 1, 3, and 3, 2, 1. These are mutually, okay, so these two Latin squares we call mutually orthogonal. What is a pair of mutually orthogonal Latin squares? It's a pair of Latin squares, which are Latin squares, and when you superimpose them, no ordered pair is repeated. Okay, what more is there to say about this? I think that's it. No repetitions, everything's good. Okay, good. Now, good. Okay, so now that we have motivated this understanding of mutually orthogonal Latin squares, let us go back to the theory a little bit. I think we're just kind of almost done. There are years when the bell rings now, and we call that good enough.
How long do you have? 'Cause it's really
10
good
minutes.
for you to,
5
you know.
5 minutes. 5 minutes, and I
have
will.
to actually leave at 4:45.
Okay, I'll be done in 5 minutes.